Hello, everyone, and welcome to the 43rd Surface Ventures keynote webinar. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and materials science education for both academia and industry. It'd be great for you all to say hi in the chat box and tell us where you're joining from. It's always nice to see where you all are, and just to check that we're coming through loud and clear. Today, it is my pleasure to introduce Professor Dr. Sabine Hild from Johannes Kepler University, Linz, and Dr. Ute Smit from Oxford Instruments. Professor Hild is head of the Institute of Polymer Science at Johannes Kepler University at the part of the Institute of Polymer Science in Linz, Austria. Her research interests mainly focus on the influence of molecular structure, composition, thermal and mechanical history in the formation of microstructures in synthetic and natural polymer-based materials. And Ute Smit is an applications manager at Oxford Instruments, Weizsäck in Ulm, Germany. With profound experience in Raman imaging, her applications and research background in scanning, tunneling, and atomic force microscopy. She's a specialist also in correlative Raman microscopy solutions. Welcome to the stage, both. Great to have you with us today.
Hello, our pleasure to be here.
Hi, nice pleasure to be here with you together.
Fantastic. So many thanks to today's partner, Oxford Instruments. We have a video recording of the main talks, but then the speakers will be joining us again once the recording is done in order to answer questions. We'll be beginning in the recording with a presentation from Dr. Smit, and then we'll be moving on to Professor Hild's talk. We'll also be releasing some poll questions and some handouts from Oxford Instruments. As we go along, please type those questions into the chat, and they'll be marked for the Q&A session, and we will address those later in the event. We're planning to go for around 60 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. So without further ado, I'm going to begin the recording. Please enjoy, everyone.
Thank you for the introduction. The topic of today's presentation is Advancing Nanoscale Polymer Characterization with Raman and AFM Imaging. Let me spend just a few words about Oxford Instruments. We are a leading provider of high-technology products and services to industrial companies and scientific research communities to image, analyze, and manipulate materials down to the atomic and molecular level. We focus on attractive segments where our key enabling technologies drive long-term growth for customers and where we can maintain leadership positions. As part of the Oxford Instruments family, both BTEC and Asylum Research bring a great benefit to the materials analysis group. The product portfolio of BTEC is shown here. At BTEC, we always focus on correlative microscopy, as shown with an example of a three-component polymer blend. The Raman image reveals polystyrene in red, ethyl acrylate, and styrene butadiene rubber in green and blue, respectively. The topography and phase images reveal the fine structure of this polymer blend, whereas the SNOM image the transparency of the blend. Interestingly, the thinnest layer, the acrylate, appears non-transparent because it does not contain the styrene block, which acts as little lens. The latest combined instrument is the RISE microscope, where Raman is integrated to the vacuum chamber of an SEM, allowing for high-resolution structural images in combination with EDS, EBSD, and all the other techniques where the electron beam is required. What is the Raman effect? If light interacts with matter, most of it is scattered elastically, meaning photons have the same energy as the initial photons, called Rayleigh scattering. A small part of the photon energy is transferred to the molecular bonds, leading to an energy shift of the scattered light. In this case, the Raman spectrum of a C60 molecule for easy visualization. This inelastically scattered light provides information about the chemical bonds present in the molecule, so the spectrum is unique to the material and allows for chemical and structural identification. This inelastic light scattering process is named after its discoverer Sir Chandrasekhara Raman, who received the Nobel Prize in 1930. Now let's see what we learn from a Raman spectrum. First of all, it provides information about the molecular composition of a material as shown on the right. We can differentiate between different polymers as the bonds between carbon and hydrogen differ in PET and PMMA. Also, inorganic materials can be uniquely identified, such as silicon, graphite, or calcium carbonate. We are able to identify polymorphs as shown with the example of SPS and SPR, where the Raman bands appear at the same position but with different intensities. The peak position and width provide information about stress and crystallinity, whereas the orientation of molecules can be studied with polarized light, as shown with the example of polypropylene. For the identification of the chemical species using Raman spectra, databases are used. TrueMatch is an integrated Raman spectral database management software which allows the comparison of the measured spectrum with thousands of spectra from databases and finds the best match, as shown in this example for paracetamol. The unknown spectrum is the one colored red. The best match from a commercial database shows that this is paracetamol. TrueMatch also offers the possibility to build a database from own reference samples. Beside identification, it is also important to obtain information about the distribution of materials. On the left, you see the microscopic image of an emulsion containing urea. Spectra measured at 3 positions of the sample reveal various organic phases. In red, an oily phase, in green, the phase containing urea, and in blue, an aqueous phase. To study the distribution of the urea containing phase, Raman imaging is required. This is done by defining the size of the measurement and the number of pixels that shall be measured, indicated here by the grid. The idea is to measure a full Raman spectrum at each pixel. Let's start the measurement. From the information in the Raman spectrum at each pixel, it is straightforward to create the Raman image that shows the distribution of the components. Pixels in red color indicate positions where we have the organic phase without urea. Green pixels show the organic phase containing urea, and the blue pixels show the distribution of the aqueous phase, which forms the matrix in this emulsion. If the sample is transparent for the laser, we can measure also high-quality 3D images with high resolution and speed. To obtain 3D Raman images, we simply measure a stack of 2D images pixel by pixel, line by line, and layer by layer. And by doing so, we obtain the Raman information of a full 3D Raman volume. If we talk about microscopy, we are also interested in the lateral and vertical resolution. A simple way to estimate and test the resolution of a microscopic configuration is by analyzing features much smaller than the effective resolution. To test the lateral resolution, meaning the resolution in the focal plane, carbon nanotubes with a diameter of a few nanometers are perfect. Here you see the Raman image of a sample of carbon nanotubes, and here a typical Raman spectrum of the carbon tubes. The most prominent peak is the G-band shown in red here. The Raman image on the left shows the intensity of the G-band and thus the nanotubes appear bright. If we look at the profile through this image, we can calculate full width half maximum for each nanotube, providing a good measure of resolution. Our example here reveals a lateral resolution of less than 300 nanometer. Secondly, the depth resolution. This is typically a bit lower because this is the direction of the laser light. To test the axial resolution, we use a graphene layer suspended on over holes in a silicon substrate. This is a schematic side view of the sample. Graphene is a monolayer of carbon atoms, making it perfectly suited to measure the depth resolution. The Raman spectrum is similar to that of nanotubes, so we can investigate the same G-band. Now we acquire Raman spectra while moving axially through the graphene layer and again calculate full width half maximum of the Raman signal. We observe an axial resolution of less than 900 nanometer. Why high-resolution Raman imaging? Let's consider a polymer blend where we measure an area of 25 by 25 micrometer square with 6 times 6 pixels and long integration time per pixel. The image and spectra we obtain look like this. Now we increase the number of pixels and decrease the integration time per pixel to keep the total image acquisition time the same. Look what happens. The image shows more details and of course the signal to noise in the Raman spectrum increases. We further increase the number of pixels and decrease the integration time, and the image becomes better and better and better. However, the signal to noise in the Raman spectrum increases. By a smart averaging of the spectra, however, we are able to reconstruct the low signal to noise spectrum of PET. The final image then looks like this with the corresponding color-coded Raman spectra. The take-home message here is, if you start with low spatial resolution but high signal-to-noise few spectra, the spatial information cannot be reconstructed. On the other hand, starting at high spatial resolution with low signal-to-noise individual spectra, spectral averaging can recover the good Raman spectra. A measure for the sensitivity of a confocal Raman microscope is to observe the first order of the silicon Raman band at about 2000 relative wave numbers. The band that appears at 2230 wave numbers corresponds to nitrogen from the atmosphere. The intensity of this band is a measure for confocality. So important for confocal Raman microscopy are resolution, sensitivity, and speed that must be achieved simultaneously. Due to its high confocality, the Raman microscope can be used to study non-destructively the layer composition of transparent foils by performing depth scans. Here an example of a foil consisting of several layers well separated from each other. The top layer consists of polypropylene, followed by an acrylic layer. The next layers are polystyrene and PMMA alterning, and the last layer is PET. Such depth scan can also provide information about defects in packaging materials or other defects like air bubbles or other gases. With my last example, I want to show you how the polymerization reaction Our liquid vanish can be monitored with Raman spectroscopy. During the polymerization, the CC double bond marked in the spectrum reacts to a single bond and therefore its Raman band decreases. Because of the transparency of the varnish, it was possible to monitor this reaction by acquiring Raman depth scans over time. In the Raman image, we can see the glass substrate in green, the liquid varnish in red, and the hardened varnish in blue. Over 24 hours, the color changes from red to blue, starting at the surface. The video visualizes this polymerization reaction. If we are talking about highest resolution AFM, Asylum Research is the Oxford Instruments branch to think of. Asylum Research was founded in 1999 by former employees of Digital Instruments. With a tremendous background in AFM manufacturing, various AFM modes were developed over the years, leading to new measuring modes and improvements in handling AFMs. The main AFM families are shown on this slide. The most flexible instruments are the MFP3 AFMs with solutions for all budgets. The Cypher and Vero AFMs stand for highest resolution, lowest noise. These AFMs are suited for small samples, including environmental control and video rate imaging. Jupiter XR is designed for wafer imaging, it's easy to use, and it's versatile and flexible. Correlative Raman and AFM measurements do not necessarily have to be made in the same microscope, especially when it comes to highest resolution or fast AFM measurements. Both branches, Asylum Research and VTech, developed software to enable easy transfer from one microscope to another. This means that different properties of the sample can be measured with highest resolution, stiffness, adhesion, dissipation energy, and many more. Now it is my pleasure to hand over to Professor Sabine Hild. She will present more details regarding this topic with applications in polymer science. Thank you.
Welcome to my presentation about advanced polymer characterization on the nanoscale using Raman spectroscopy and scanning force microscopy imaging. My name is Sabine Hild. I'm from the Institute of Polymer Science at the Johannes Kepler University, and I'm very happy to present here the work of my former students Claudia Leimhofer and Saskia Dahlberger. Our research topic are polymer composites. These materials gained increasing amount of interest in application and research because we can have materials which has properties which cannot be achieved with pure substances on its own. And we have a wide range of manufacturing options to get different type of composites, for instance, layered composites, such as gluing or welding, 3D printing, and on process level, we can use co-extrusion or co-injection to get new materials. All of these materials have one thing in common. They have high mechanical and chemical stability. To get this, the adhesion between the different components is a crucial point. Since I think we have here not only surface people, I would like to define what is adhesion. Adhesion are the sticking forces at the contact of two different or identical substances due to molecular forces. And there are different mechanisms available which leads to the adhesion, such as mechanical interlocking. When you have rough surfaces, you can chemically bond polymeric material to surfaces. You can adsorb polymers and have an adhesion due to the formation of non-covalent bond. And what is important when you have polymers in contact with polymers are interdiffusion. The theory of interface formation due to interdiffusion has been suggested by Wojcicki in the middle of the last century. He proposed that compatible polymers which are getting into close contact can adhere due to the interdiffusion of molecules at the superficial layers. Therefore, a transition zone will be formed where new entanglements between the intermixing polymers will be formed. This transition zone is called interdiffusion layer. The strength of the interdiffusion layer results from a complex interplay of diffusion and viscoelastic properties of the polymers. Influencing parameters have been shown to be process parameters like temperature and contact times. On one hand, on the other hand, we have material parameters such as the molecular weight or the molecular weight distribution and the compatibility of the polymeric material. Polymer interfaces can be formed under different conditions. One example is the co-extrusion process. This is an industrial process where you directly join two molten polymers to form multi-layer structures like packaging foils, bottles, or pipe, as shown here in the sketch. Here, interdiffusion happens at moving interfaces. Thus, additional factors have to be taken into account, such as interfacial shear stress and chain orientation. Although the technique of co-extrusion is used since 50 years, the mechanism of interlayer formation and all influencing parameters are still under discussion. There are two different models proposed, one in the beginning of the 90s by Kim and Han, based on theoretical consideration. They suggested a decreased diffusion coefficient due to the chain orientation under shear. In contrast to this, in 2015, the group of Zhang and Lamnabar showed in experimental research that higher interfacial layer thickness occurs during co-extrusion, and they thought that it is due to a positive effect of the intermixing at the interface. Nevertheless, it's not clear what is really going on for the interface formation under shear condition. This is especially because there is a lack of knowledge in high-resolution chemical characterization of the interdiffusion layer. In particular, the distribution of the components within the interface has not been carefully investigated. And this is why we thought maybe can high-resolution chemical characterization by confocal Raman microscopy provide new insights into the mechanism of interdiffusion layer formation under production conditions. Our first aim is to prove that confocal Raman microscopy is suitable to study the interdiffusion layer. Therefore, we perform static diffusion experiment using highly compatible polymers. Our experiments are performed under controlled diffusion conditions in a heating chamber where we mount 2 millimeter thick discs prepared by injection molding. In a nitrogen atmosphere, we preheat the individual polymer discs without bringing them in contact until they get the desired temperature. Then we bring them into close contact for a given time. Contact times are chosen between 5 and 120 nanometer at fixed temperature of about 200 to 260 degrees C. These seem to be very high temperatures, but these are the temperatures which are relevant for co-extrusion experiment. Therefore, we use this. When we reached the desired time, we quench the sample down, meaning cool them down with maximum capacity. And then we prepare smooth samples using a cryo ultramicrotome, where we polish cutted samples at minus 40 degrees C with a glass or diamond knife, so that we get these nice smooth surfaces, which we can then use for further investigation. Our highly compatible model system consists of PMMA on one hand and styrene co-acrylonitrile, a random copolymer which contains 19% of acrylonitrile. On the other hand, both polymers are amorphous polymers. They have a comparable glass transition temperature of 95 or 105 degrees. We choose samples which have similar molecular weight and a similar molecular weight distribution to avoid any further influence of different molecular weights. From the first glance, when you look to the polymers and you see that you have styrene and PMMA, they are normally not compatible. Why can we mix PMMA and SAN? Because in the copolymer, the SAN, styrene acrylonitrile, there we have a phase separation which favors the incorporation of PMMA. Thus, we get a very good compatible system for further investigations. The Raman spectra of our components looks like this. We have the fingerprint region where we find for the PMMA one band which is characteristic at 7032 reciproc centimeter, which can be assigned to the stretching mode of the carbonyl bond in the ester group. On the other hand, we have the SAN. Here we also have one band which is characteristic. This is the band at 2240, which can be assigned to the nitrile group. Now we can perform Raman imaging line by line, recording Raman spectra. We choose 4 points per 1 micrometer, about 50 to 100 microns in the width, and then also in the second direction, in the line direction, we can choose if we have the same number of lines or not. Nevertheless, when we after recording the Raman spectra, we have to analyze the data, and therefore we plot a sum filter of the nitrile group and get this image where we see the SAN as the bright domain on the right and the PMMA as dark domain on the left. What's obvious here is that we have a very nice sharp boundary between the polymers, and when you look a little bit more into details to the film, you see that there's a blurring of the color at the interface, indicating that we have a mixture here of the polymers in this region. Now the question is, how can we learn more from the Raman imaging about diffusion characteristics? Therefore, we have to analyze the images. Image analysis using the sum filters has shown not to be suitable for a quantitative analysis of the composition, meaning to extract concentration profiles along the interdiffusion layer. On the other hand, we could choose component analysis for imaging. Here, we have a technique which based on the linear combination of spectra of the pure components with an equation like is shown here. For each point in the spectrum, we have a hyperspectral data set which contains the matrix of the basic spectra, SAN and PMMA. They have a mixing factor and an error spectrum. What is important for our analysis is this mixing factor, because we can extract it from the analysis, and when we have the intensity distribution of this mixing factor will lead to nice images where we can separate the individual materials. What we are interested in is to get a little bit more quantification. Therefore, we assigned a mixing factor. So for each point in the spectrum, we want to have the mixing factor of the individual polymer in relation to the total mixing factors of both components. But this is not enough to get quantitative data which are relevant for chemists. We want to have weight percentages. Therefore, we have to correlate the mixing factors to the respective weight fractions, and we have to measure an external calibration curve. Therefore, we prepare binary polymer films with increasing amount of one of the components. We solvent cast them on a surface and then record Raman image, similar to this what I showed here. And then we can determine an average mixing factor coefficient from the Raman image, just calculating an average spectrum of the whole image, which now contains known amount of the two polymers And then with this knowledge, we can extract the mixing coefficient for the two polymers when we just have the one mixing coefficient for one component and we have the known weight fraction. We did this for PMMA and SAN, and then for every pixel of a Raman image, the composition can be determined, and this allows us now to evaluate diffusion profiles. From how to get from a Raman image to a diffusion profile is not that straightforward as we thought in the beginning. We have the spectral correlation distribution of the PMMA SAN mixtures. We record, I call them reduced Raman images because we have high number of spectra along the line, but only 20 lines are recorded. Then we perform the component analysis and we get the images for the mixing factors. These images show one thing, that we have here an interdiffusion area which not really fits to each other. Therefore, we plot all the lines and we shift every line we recorded to a relative interface position, which is our reference position 0 and has a weight percentage of 50% of PMMA. Then we average over all the lines and then we get one mean profile which we can use for further analysis. So this means we have to do a lot of steps for the data analysis, but this helps us to perform time-dependent interdiffusion studies as shown here, where we have a set of diffusion experiments which are performed at constant temperature of 240 degrees. What we see for both the line we plotted for the PMMA and for the SAN, we see a broadening of the interdiffusion profile with increasing contact time, indicating an increase in the interdiffusion layer thickness, which is quite okay, but it's even here not a value we can correlate with physical quantities. Therefore, we would like to evaluate the interdiffusion layer in a little bit more details. And for this, we have to specify limiting values for the evaluation. Because if you look to the individual interdiffusion layer profile, you see that there's a very smooth transition from the pure polymer to the interdiffusion layer. Just we decided to use boundaries of 5% and 95% for the evaluation to get interdiffusion layer thickness for all of the samples. And now we can plot the interdiffusion layer thickness, which is correlated to a weight fraction to the contact times. And we see a nice smooth increase of the curve. Now we can look into a little bit more detail to our profile. And even if we have here our 0 position, what we see is that our interdiffusion layer is asymmetric. The profile is smaller on the left than on the right. This indicates that we have different diffusion properties of PMMA and SAN. And we analyzed also the layer thickness for the individual layers, and we see when we assume that on one hand SAN is diffused into the PMMA and other way around, SAN has a lower diffusion property than the PMMA. Now we have to verify that we really have diffusion, and when we talk about diffusion, normally we talk about fixed diffusion, meaning that the thickness of the interfacial layer is proportional to the square root of the time. Thus, plotting the results from the slide before versus the square root of the time, and what we see is that we have nice lines. This confirms that we have fixed diffusion, and this allows us to determine the slope of the lines, which reflects the diffusion constant. We analyze the total diffusion constant, and since we have this asymmetry, we also determine the diffusion constant for PMMA in SAN and PMMA. So this was our first result, and we said, okay, it's quite satisfied with this. I can give you a first interim conclusion. I hope I could show you that confocal Raman microscopy is a suitable tool to analyze the interdiffusion layer of polymer composites with sub-micron resolution. We could estimate the chemical distribution of the compounds along the polymer-polymer interface, which allows us to elucidate time-dependence diffusion profiles with a very high resolution and a very high reproducibility. And we could determine different interdiffusion constant for the different polymers. But we are not sure if it's really the interdiffusion constant, because with all the techniques, we are not able to allocate the initial interfaces when we started. On the other hand, we have some limitations in confocal Raman microscopy. Here, the lateral resolution is limited due to the laser wavelengths and optical components which we used. We found a lower resolution limits for very sharp boundaries in a range of 250 to 500 nanometers, which does not allow to investigate very thin interdiffusion layers, as they are formed in incompatible polymers. And what we are not able to elucidate is differences in the polymer structure. Therefore, it seemed to be a good idea to use a second technique as a complementary. We choose scanning force microscopy as a complementary technique because we can apply the dynamic imaging techniques to investigate the microstructure of polymeric material due to the variations in the sample height, as it's shown here in topography image of a polypropylene spherulite. And when we additionally record phase shift images, we can allocate polymer nanostructures due to differences in the chemomechanical material properties. So we can enlighten here crystalline lamellar structures. Let's see if this technique is. Here are AFM images of our pure materials, PMMA and SAN. The sample we used are the ultramicrotomy polished surfaces, but now we not investigate the interface, but the bulk region. And what we found for the PMMA was not as expected a very smooth surface, but we found in the PMMA a second phase consisting of spherical structures with a diameter of about 100 nanometers. Since the Raman spectra does not show any additional polymer bands, we assume that is an acrylate-based polymer which has been added to the PMMA to improve its processing conditions. On the other hand, we have the SAN. SAN is a random copolymer, which also should be smooth and homogeneous, but even here we see that phase separation occurs. We have brighter and darker areas, so we could see the different domains of acrylic nitrile and styrene, but this structure is not that pronounced in the phase image, so we could use phase images for discrimination of the two polymers in further analysis. Now, how does our interface looks like after static diffusion of 5 minutes at 240 degrees and 60 minutes at 240 degrees. First thing, what is could be seen is that there is a sharp boundary between the two polymers, the PMMA and the SAN. Second, at the PMMA site, we do not see any significant change in the phase shift, even at the boundary. While on the SAN layer, we could discriminate at least 3 different regions within the phase shift. First, we have a very bright regime on the right, as I show here. Here, the phase shift is about 5 degrees, which relates to the pure SAN. Then we have this intermediate regime. The width of this is between 15 and 17 micron, which correlates to the values we found for the total interdiffusion layer thickness obtained from Raman imaging. Gives a good indication that we have here the interdiffusion layer due to the intermixing of the two polymers, hopefully. And then we have a third dark regime This indicates a second diffusion zone. The width is after 5 minutes 3 micron and after 60 minutes 10 microns, and this is in good accordance to the asymmetric shape of the diffusion profile. But it's still not clear what is going on the molecular scale. Here further investigations will be necessary. Since we've proved that Raman spectroscopy and scanning force microscopy are suitable to investigate the interfacial layer, we would like to compare what is going on the static and under shear induced interdiffusion. Static diffusion I've shown you. This is our co-extrusion experiment. We used a special 2-layer co-extrusion demonstration die, which allows to produce sheets which have sample dimensions in the range of 15 micron and a thickness of 4 micron. We could systematically vary the processing conditions in a way that we adjust the output and the position of the interface, thus varying the contact time and the interfacial shear stress of the experiments. Our first goal was to study the influence of the contact time. Therefore, we prepare samples under similar interfacial shear stress. What we saw is that there is an increase in the interdiffusion layer thickness with increasing contact time. And the average interdiffusion layer thicknesses are 3 micron for contact time of 10 seconds and 48 seconds contact time leads to 6 microns interdiffusion layer thickness. To compare the results of static diffusion and co-extrusion experiments, we determined contact times to reach the same interdiffusion layer thickness for a given temperature. We choose a thickness of 6 micron, and this is reached after 48 seconds in contact for our co-extrusion experiment and after 300 seconds for our static experiment. This shows that with co-extrusion, you achieve the same interdiffusion layer thickness with much shorter contact time and proves that shear stress improved diffusion properties of the polymeric materials. But what is the regime of this impact? Therefore, we perform also an experiment where we increase the applied shear stress and have the contact time constant. So have the contact time constant, increasing the shear stress by a factor of 10. What we see is there is an increase in the interdiffusion layer thickness, but this increase is not related to the same amount as the shear stress is increased. This gives us the first hint that there's also an influence of the chain orientation into the interface formation. Our last topic now is to characterize the interfaces using scanning force microscopy. Therefore, we compared samples are in contact for 10 seconds at 240 degrees C and 30 seconds for 140 degrees C. What is similar that we have the two different polymers, which could be nicely discriminated. But when you look into a little bit more detail to the boundary between the two polymers, this is not a straight line anymore, but it becomes wavy. At the PMMA side, we do not have a significant change in the phase shift, similar to what we observed for the static experiments. On the SAN layer, what we see is that the phase shift at the boundary is reversed to what we observed in the static experiment. And now a bright zone appears at the interface, which has a width about 3 to 5 micron, which cannot be really correlated to the interdiffusion of the PMMA. So this is one point which is still under investigation. What is also possible to see on the first glance that within the SAN regime, a grainy structure appears, indicating that there is a phase separation within the copolymer, which will be caused mainly by the process conditions. With this, I can come to a final conclusion. I hope I could show you that confocal Raman microscopy is a suitable tool to analyze the interdiffusion layers of polymer composites. We could estimate chemical distribution of the components with in the polymer-polymer interface so that time-dependent diffusion profiles can be obtained, which proves that we have fiction diffusion. When we compare diffusion experiment performed under static and shear conditions, we see that shear flow increases diffusion, but we have also to take into account that chain orientation can have an impact into the interdiffusion layer thickness. As the complementary technique, we use scanning force microscopy, which is a suitable tool to provide additional microstructural and physical-chemical information about the interdiffusion layer, which allows us to allocate within the SAN region different diffusion zone, and we do not see any mechanical change within the PMMA layer. When we have different process conditions, static and shear, we could also see that the microstructure of the interdiffusion layer has to be changed. But to correlate all this, the next step would be to do correlative Raman AFM imaging, which we hope will give further insight to the diffusion behavior of the polymers and the formation of the interdiffusion layers. With this, I would like to say thank you to our cooperation partner, Alexander Hammer and Wolfgang Roland, who provided us the co-extrusion samples. The whole project was in collaboration with two companies, Poloplast and Engel, and was funded by the FFG within the framework of the Competence Center Proto Future and Chase. And all of this work was not possible to perform without all the members of my institute. And with this, I would like to close and say thank you for your attention.
Okay, that concludes our recording of the presentations for today. There's some fantastic insights there into both AFM and Raman. So thank you very much to both speakers for preparing such excellent presentations and recordings there. So we'll now invite both of them back on stage. Whilst they are coming on stage, a couple of things I would like to highlight to you. Right now, I'm going to make available the attendance certificate link, which is now available as a featured action. You can find that there in the bottom left of the screen. Welcome back to the stage, Uta and Sabina.
Hi.
Excellent. We're already getting some questions in. Before we take our questions, one quick thing. Excuse me. For anyone who wants to read more about some of the work Professor Hill talked to, I'm now putting a link to papers in the chat. So please go ahead and look at that at the bottom of the message. This is an open access paper, so please, everyone, go and have a read. Very easy to get access to. Thank you very much for sharing that. Okay. With our first question. So I'll read it out, and then we'll see who may be best to placed to answer this one. So from Coward, thank you for your question. Do you think the degree of polymerization of each polymer could affect the depth of diffusion and the resulting bond strength between the different layers of contributing polymers? A very good question.
Yes, there's a strong influence. This is why we choose the same molecular weight, but we had also others polymers which have higher or lower molecular weight, and we see that there is definitely an influence.
Okay, thank you. Whilst we're waiting for some other questions, I have a few of mine just from curiosity about the talk. So I'll just sort of begin with a general one about resolution and Raman imaging. That's okay. So how would we go about improving resolution for Raman?
Well, as we all know, Raman imaging is an optical method, so we are diffraction limited and we cannot go beyond physics. However, what you can do is you can decrease the excitation laser, which leads to an improvement of the resolution. On the other hand, if you go completely to the blue or UV, you will have to deal with fluorescence,
Mhm.
which again is hiding the little Raman signal. And probably you may not know, but what you put on the sample in terms of energy laser, only a millionth part is Raman active or comes back as Raman light. So if you use a laser which excites fluorescence in your sample, you may not see this little light, which is based on the molecular bonds. So far, the most used laser is the 532. I think Sabine agrees with me,
Yeah.
which is a kind of like optimum between excitation and what you get back as Raman signal, a good compromise between fluorescence and resolution. Thank you
And
for the question.
Thank you.
You
just
can add,
maybe
Sabine.
I can add maybe something because we had this interdiffusion layer and we got these questions from the colleagues. And what we did is we prepared a sample with polystyrene and PMMA, which are not miscible, but they glue together. And then we just really checked what is the thickness of the boundary layer. And this is where I get this 200 to 500 nanometers. It depends a little bit, yeah, on the polymers, how effective they are. But this was our test to see what is the really resolution limit for our samples.
Okay.
With the green laser we used.
Okay, thanks. Yeah, great. And thank you. I had no idea about the actual proportion of amount of Raman excitation as opposed to fluorescence. That's really interesting. I did have a couple of my own samples from a little while ago that did fluoresce, so it's good to know.
So as soon as you excite fluorescence, you may have to go to higher wavelengths, which of course then is decreasing the resolution. And some samples are just not cooperative, I would say.
So that kind of brings me on to my next question. So would that be the case where you would have multiple lasers for a Raman microscope then?
Yes.
Yeah.
Okay.
Yes. So that's the reason to have more than one laser on one system, just to have the choice to move out of the fluorescence regime of the sample.
Yeah.
And sometimes you have to go to higher wavelengths. It depends a bit also if the samples have, for example, a reddish color, then you want to go more towards the blue, so lower wavelengths. I'm thinking here, if you look at shells, for example, which have this brownish color, you may not get too much out of them if you use the 532 because you get into the luminescence phase. However, if you have dark samples like a lot of carbon, then you may want to go to lower energy or higher wavelengths and try to get your images with a higher wavelength but lower resolution.
Yeah. Especially if you use biological samples, you excite fluorescence in a range between 400 and 600 nanometer. So there, the red laser is more suitable. And what we learned also for the polymers, there are often additives which are also fluorescing colors they add if you have industrial samples which can be get fluorescent when you use the green laser. So we switched between red and green, and we try always to find the best compromise for imaging.
Yeah. I was just about to say, it seems like it's very much a case of find the compromise and figure out just maybe not necessarily the absolute best, but what's just the optimal wavelength to use for a specific sample. Okay.
That's why we invite people over if we have unknown samples to our facility, because we have the full range of lasers most of the times available, and then can move maybe from one instrument to the other, because we cannot equip all the microscopes we have at VTech with all the lasers available, and find the optimum before people are interested in going into the purchasing state.
Okay. Thanks for the information. We still have a little bit of time, so if anyone else would like to ask any questions, please do type those into the chat. Whilst we're using it at the time, I'll just a couple more questions from me, just from my interest. So at the end of the talk, Sabine, you talked about using combined Raman and AFM. So what would be the benefits of using that? What would you get out of combining these two techniques?
What we had, so we started with the, just for the samples, we started with an idea. We said, okay, we bring the samples together and we have diffusion into both sides. And we analyzed the samples like this. And what we saw is that it's an asymmetric profile. So therefore, we want to prove if our idea is okay. When we combine this would be the possibility to really see where's the boundary, where we have the materials which we can nicely discriminate, and then overlay this with our chemical profile. But it's a compromise again, because in this case, AFM will take, to get an AFM image, it will take 20 minutes at least when you get very high resolution, but get high resolution Raman images can take much longer. So it's a question when we combine this, if we get all the information, and we prefer to do it on different setups and then bring it together. But these are the first samples where I think it's worth doing it at the same time, just to prove the concept, not for it's just for our samples, not for all of the samples is worth doing it, but here we get a little bit more information.
Well, on the other hand, we should also consider the fact that with the AFM, you are looking really at very high resolution in the nanometer range. And if you consider taking simultaneous Raman AFM images, there is a lot of wasted time of heating of the cantilever, of a lot of little features which one has to consider when you want to do this simultaneously. And beside that, you may have to use transparent samples to do Raman from below and, because if you try to squeeze a cantilever between objective and sample, you give up numerical aperture, which means you give up already Raman resolution, which is not that perfect. So should I go on? I think time is almost over. I should rather stop.
I mean, all great information. Thank you. I think just in the interest of time, since we have our I see one final question from the audience, and then we'll draw the draw the webinar to a close. So we have two questions. Do you both mind if we answer these two, and then we and then we'll close out? Excellent. Right. So we have one from Shirish. I hope I'm pronouncing that correctly. Who asks, can Raman spectroscopy be used for analyzing the wear patterns in engine components like cams or tappets?
Yes, it's possible. We did it, but the point is the samples are huge. We got samples of this size, and you have to prepare them so that you get small samples out of it. But it's possible.
I'd imagine the sample preparation is really the most kind of awkward bit of that. With the sort of wavelength that you're targeting for the sort of films that you would deposit on engine components, are there any fluorescence considerations, or is it a relatively simple?
It's often it's the metallic stuff what people are interested in. So there is no problem with fluorescent, and it's question about the surrounding. What is what they're working with? So we tried first to check what they have as possible oils or something around, and then we said, okay, it's worth trying it. But industrial samples could have a lot of different things, and it's always necessary first to check on the fluorescence and then decide it's yes or no. Because it's also possible with AFM to analyze the surfaces. We did it. I had a student who did this with a tiny AFM, which could be put on top of a machine. So this also works.
Okay.
Yeah, but in this case, it was not a combination, but it's possible to do this.
Okay, got it. Thank you. Talking about combinations, our final question from Umer, I hope I'm pronouncing that correctly. They ask, is there any advantage of combining Raman spectroscopy with AFM for polymerization?
It's a question, what do you mean with polymerization? You can follow polymerization with the Raman. With AFM, it depends on the system, because if it's a liquid system, you will not get any information. You get, because it's liquid, the cantilever will tap inside.
Yeah.
So what you can get with AFM is, for example, transformation. So if you heat up the sample or cool it down, then you can see changes of it. But really, like I showed, the polymerization process over time, like I showed with the vanish, that is probably not really possible with the AFM.
You
I hope this answered your question.
Follow the phase transitions, yes. And you can do this, but you need, for the polymerization, it's better to need other techniques to follow polymerization. When you want to see mechanical changes, for instance, if you have cross-linking, you can combine Raman also with other setups like rheometer or something like this. And this is possible, but and it's the question what you want to see.
Yeah, that's great. Thank you. So I think with that, we're now just over our hour of time. So let's draw this keynote to a close. Thank you both very much for your great presentations. Thank you for preparing the recordings. Very neat, very well done. Thank you. Thank you very much to Oxford Instruments for partnering with us for this presentation. It's always great to work with great partners, and we wouldn't be able to do what we do without our partners. Thank you to everyone in the audience who attended and for asking such great questions. Thank you very much. As a reminder, please do visit our website, surfaceventures.org. You can see some of the other things that we do. You can find our archive of talks. You'll be able to see our posts on LinkedIn as well. Please do look at those. You can find our newsletter there. If you're interested in our next keynote, I've made that available on screen now with Dr. Amir Katirik from Imperial College of London. So very much looking forward to that talk on the 28th of November, 3 p.m. GMT. So please do register for that. And finally, I'd just like to say, if you found this useful, please do take the time to advertise these lectures to your friends or colleagues. It's always great for us to keep growing our audience and continuing to do what we do. So with that, I'd like to say thank you very much. Thanks for joining today, and have a great rest of your day.
Thank you.
Thank you very much.
Thank you. Bye.
Thanks, everyone.
Bye.
Goodbye.